For the topic on distributed distribution grids. I have the pleasure to have a kind of an overview presentation with regard to integration of variable renewable energies in distribution networks. And I'd like to give you at the very first point a light overview about experiences we had in Germany. So I think it's important to share the international experiences because, to be very frank, in Germany we made a number of mistakes and you shouldn't do them again. So I would really recommend that. And so maybe I can give there some advice how things could be optimized, so especially with regard to grid codes. We then also have a number of questions of how the future distribution grid actually looks like, and so there are a number of buzzwords going on grid modernization, smart grids, bidirectional grids, and distribution system operator, active distribution system operation. So I'd like to give some light into this area, and I'd like to present a kind of a phase model that shows the different steps into high penetration distribution grids. So at the very beginning, a number of slides. Some of you might have already seen in other layouts and so on. So in total, we have in Germany more than 100 gigawatt renewable energy capacity installed. This is more than our load. So the load is between approximately 35 gigawatts to 85 gigawatts, and it is also more than fossil fuel installations we have today. So there was a steep increase, and so it was quite a challenge in certain time areas to manage this. We have, caused by this, we have situations in the national power system where we have nearly 100% power generation for the load from renewables. Of course, just a couple of hours a year, but nevertheless. And you have already seen that in several presentations. So I'd like to focus really clearly on the distribution grid, and there's an important issue that in Germany we have a kind of an international speciality that the distribution grid is not only low and medium voltage but also is high voltage, so 110 kV. And so that's why we can say that approximately 95% of the renewable energies are installed in our distribution grid. So this is really a challenge as it's turning the power system upside down with regard to the supply system. And so this is causing, especially in the distribution system, significant changes. This is now a huge list of different numbers. What I'd like to show you here is that we have if we go here to the left row, so these are states in Germany. And you see there is a big difference with regard to the share of renewable energies in these states. So this is approximately the high voltage level, I would say, very approximately. So that means we have, with regard to energy, we have the situation that in some states we have approximately 10%, but we also have here, for example, Brandenburg, which has approximately 80% energy-wise renewable energies. And this is, well, the aim of the national target for 2050, which we already can see in certain grid areas. If we go in the middle, column, we can see this is one size below. So within Brandenburg, we have different areas, and we can see that there are energy-wise areas. This is approximately the size of a medium voltage grid, where we have more than 200% renewable energies in there energy-wise. So the double to threefold production compared to the consumption. And this means we have approximately tenfold capacity of renewables compared to the peak load. So this is just for giving an imagination about what will happen in the future and the diversity. And so in one of them, it's mainly wind. In another, it's a share of wind and photovoltaic. So that means we have not only supply grids, but we have, so where the consumption is supplied, but we have generation grids. This is reality, and this is changing, of course, in the night, for example. If the PV is out, then we have consumption in this grid, and during the day, we nearly only see production. So this is just a measurement in one of low voltage grids where we have a peak load of 130 kilowatt, and we have a photovoltaic capacity of now more than 1,200 kilowatts. So it's a factor of 10 just by reality. So 80 households and 60 PV systems. So you can look at Google Maps and you can see blue rooftops. And so this is, of course, impacting on active power flows as well as on the voltage. What we also can see is, of course, with that regard, reverse power flow. So now I'm voltage level higher. So this is a high voltage, medium voltage substation in a rural area in Bavaria. And so you see in 2009, we are in positive values. So it was only consumption nearly. And then we had the very dynamic years of PV production, of PV installation enhancements. And so we see that within only 1 year, it just extended to the negative values. So it was reversal power flows to the high voltage grid. And until it doubled on that size. So now the dominant factor in sizing the substation is not the load anymore, but the generation here. So now you could argue, well, this really brings danger to reliability. So this is now the national average. But you see over the last years, even we had a steep increase, a threefold increase of renewable energies, and I said mainly in the distribution system. We can see that the SAIDI, which is a reliability index for outage durations, and so what we can see is that the index is going lower. That means reliability is increasing. So in this case, you can say that you can increase significantly the penetration of renewable energies, and in the same time, of course, this goes in hand moving from overhead lines to cabling and so on, which is also one driver here. So you can increase reliability of the grid, even integrating huge amounts of renewable energies. Another issue that is going on is that we had in 2012 the grid parity for households. So what you see is the household tariff. This is increasing, and we see the feed-in tariff for photovoltaic systems, which is steeply decreasing. And in the crossing section, we have the grid parity. And this is changing the situation in Germany significantly. So there's, since 2012, a huge interest in doing self-consumption and not only PV production. And so nowadays, many of the PV systems installed in residential units even get PV battery systems. So I would not say that it's really economic, but at least it's a reality. So 60,000 PV battery systems. And if you want to have about half of them to have support for the investment from KfW, and there they are really grid supportive, because the requirement is that not more than 50% of the nominal PV capacity is allowed to be fed into the grid. So this means in the calculation for the grid operators for planning purposes, they could even calculate approximately 200% more PV installations in the grid due to this condition. We had to tackle, of course, over a longer time frame, the design of the grid code. So we were looking, of course, in all the relevant dimensions: frequency control, voltage control. Very important is also the security actions, which means active power curtailment possibilities. And what I just said with the batteries and the local consumption, this is another issue that is going to be addressed. So starting first with the frequency support scheme. So you have heard also yesterday about the 50.2 hertz problem. So inverters were getting parameters for over frequency protection that were not oriented on stability, but more on that we don't have sufficient PV systems, so it will not be a danger, but it was underestimated. And so there was a huge retrofitting action that cost hundreds of millions of euros of costs, and hundreds of thousands of PV systems had to be retrofitted. So this is a mistake. Please don't do it again. So ensure that your renewable energies stay connected to the grid, even in under-frequency situation. And be sure that if you come into over-frequency situations, that it's not disconnected, but that it's dynamically decreasing and thereby supporting keeping frequency stability. Another issue is voltage stability. This is mainly with regard to grid extension reinforcement costs. So here's just a small example of a number of grids that were analyzed. And so you see at the lower bar, you see the reference. So if we don't use any voltage control, and then you see a number, I will not go into detail, of different ways of voltage stabilization, of limiting voltage increase, so to prevent voltage violations just by local control measures. And you can see that in average, not really depending on which one, so there are slight differences, but more or less 50% of the costs in the studied grids and under the assumptions were prevented as grid reinforcement costs or cost for grid, also grid operation. So that means it's really worth, due to cost efficiency in applying voltage stabilization functionality by reactive power supply, or of course also active power limitations, or online tap changes in transformer stations. So there are different ways, and it's a topic for itself. So going to the active power curtailment, actually, so we have seen over the last years a steep increase of curtailment measures. And so as you see, this is a really steep growth. So a couple of years before, it has not been seen as a relevant issue. Now we are in numbers of 3% of the annual production of renewable energies is curtailed because the grid is not able to absorb it. So the grid is delayed in being reinforced, especially in transmission. And so this is important to get a control capability of distributed generation, also in distribution system, even down to medium and low voltage, to have a sufficient amount of controllability of this generation. So if you have it installed and you cannot control it, you have a problem in case of system security issues. So we have gained in Germany 100%, nearly 100% control capability of wind. At PV, we still have here a larger area of about 30%, which is not controllable yet. These are, of course, low voltage systems of smaller size, where it's difficult to get, after having installed them, the communication and so on to a cost-efficient way. I'm not going into the storage issues. This is a topic for itself. And so finally, we have made a couple of mistakes in integrating into grid codes requirements for controlling active power control and frequency stabilization parameters early enough. So do that at the first possible time in your grid codes, so you don't need to do any retrofitting. Coming now to the question of what is the future of distribution grids actually. So you have all the buzzwords I already mentioned. I will especially go into one topic, which is a kind of a stage or phase model we have designed in the PVPS Task 14. It was also mentioned from the IEA presentation yesterday morning, and it includes the idea of having a penetration consideration of the transmission system, which is here the vertical axis, and the penetration on the DSO, which is on the horizontal axis. And so we start actually at low integration values, and so there are some issues. You need doing some reinforcement measures. That's all. That's not a big deal. Then you're coming in certain distribution grids. You come into significant measures you have to do. So now you need to think about cost efficiency, how to do it in a cost-efficient way that you are not oversizing and making some costs maybe in that way. So here, of course, you already should have prepared your grid codes in order to be able to react in case there are any issues from transmission side concerning frequency or system security issues. But if you go to phase 3, so you have a very high penetration in the transmission system as well, this is then really going into a question of rethinking the operation of the transmission system as well, to redesign controls. So now you have the inverter-dominated grids, so you have to identify new control functionalities, and you have to design the system built on renewable energy. So ancillary services need to be provided by renewable energies and so on. So this is really a big deal in transmission as well, and in the coordination between distribution and transmission. So we are in Germany, we are here at phase 2 and reaching into phase 3, let's say. So we are somewhere here, and so between 2 and 3, I think India is somewhere between 1 and 2. So we see that in the discussions we are having. Very important in that domain is to consider megatrends. And megatrends, this is really the topic. First, we have our political objectives, which is we want to increase renewable energies. So this is decarbonization. We want to do it nearly everywhere around the globe. Then the question is where to install renewable energies. So there is a certain trend to have it decentral. So it's decentralization. So if we want to do that, we have to deal with the distribution system, and this is the major topic here. So beside of, so this is now the first two. Now we can think about digitalization. So we can integrate high shares of renewable energies in the distribution without digitalization. So we have done that in Germany already, and you have shown you the figures, without digitalization in distribution. So there's no control up to now really in detail and visibility for distribution system operators in low and medium voltage. It's just starting. So this is a separate trend, and it is not a pre-requirement for installing renewable energies. It's an additional step. And the fourth mega trend, it's kind of autarky, which means that people, if they have a photovoltaic system on their rooftop, if they drive an electrical vehicle, they come to the fancy idea of providing their energy for themselves. They can do it, but not all the time, so they are still dependent from the grid. And this causes a new mega trend, and we need to think about how to do that. So there are things are on cellular microgrid approaches and so on. This is even more in the future. So you need digitalization before you think about that. So it's the next step. So we have to think about that. We can use this kind of a structure also with regard all the different areas we talk of. If we go from a network operator to a system operator, and so we are already, we can even distinguish between a first category of DSO 1.0 and a second version, let's say. So in Germany, we are talking at the moment about the role of a DSO 2.0. So we are already talking about the third phase, actually. So we talk about system stability, grid codes, ancillary services. We talk about grid integration with regard to planning, so how to increase hosting capacity, grid reinforcement, about customer integration, including also storage, and we talk about what I just said about microgrid structures. So I will just go into one example, how to consider that. So this is now quite something I'd just like to explain. So on the left-hand side, we have the topic of renewable energies in distribution grid. So we are talking now about the stability, control, and operation. And first, in the first phase, we have to guarantee system stability with grid codes. So everything is with grid codes, no? Nothing more. You need to design voltage stability, frequency stability, system stability with active power containment, also some requirements for power quality and protection. And this is sufficient for phase one, and actually this is the so-called plant readiness level. So all the systems you install should be ready to do that, even if it's not required at the first phase, but you need it in the next phases, and then it should be prepared. So then the next phase actually is somehow you need to control them. And so the DSO also need to get ready to control them. Yeah? So now we need to have ICT, control center capabilities, so that the plants ready in phase one can then be controlled in phase two. And then in phase three, this is then going into responsibility change. So the DSO takes a major responsibility in the system operation. So ancillary services come from the DSO and have to be provided to the TSO. So this is next phase of being in very high penetration levels. And systems are inverter dominated. So the control structure based on synchronous generators has to change. And we can also consider that with the digitalization trend, so on data, information, communication. And first is to have, again, the plant readiness. So PQ values need to be able to be controlled remotely, but it's not necessary to control them everywhere. So it could be that you install a number of those plants in your system without controlling them. It's okay. But you need to control them later, so they need to be prepared in a digitalization sense. So then it's a control center again, as just said. So it's mainly observability to get, and also to have congestion management, volt-var control. And phase three, then we are coming about, we want to do it more detailed. We want to have a better transparency in the system. So we are talking about smart metering, forecasting, in the low voltage. Yeah? So I'm not talking about high voltage or transmission. So there it's a must at the very beginning. We have to do a DSO-TSO coordination. We are talking about smart grid, smart market issues. So it's about cost efficiency. It's about improving, about digitalization. And so this is mainly the idea of these different phases, and you should be aware of where you are and what you have to be in preparing. So if somebody is interested more on that, I can go into further discussion after this event. Now I have limited time, so it's the same thing on planning, customer integration, microgrid structure. So you can apply in all these areas, you can apply this phase model. So you are doing what is required in your situation. So coming to the conclusions, what I just presented. So first phase, also according to the experiences we had in Germany. So we start integration renewable energies. We have to do grid extension, where needed, but no deal, we just do that. Important is plant control readiness to guarantee system stability and to guarantee operability at a later phase. Phase 2, here we gain in certain distribution grids, not everywhere in the grid. So some distribution operators are the winning ones. They have a lot of renewable energies, and others are the losers in that sense, not having, or you can see it the other way around, depending on your perspective. And there you need to have the DSO readiness, planning and operation with large-scale renewable energies. Phase 3, finally, is now you have a penetration throughout your power system on distribution and transmission. So everything has to be built on renewable energies, facilitate them doing everything which you have done before in other terms. Of course, you need storage as well. And, well, I leave the topic, microgrids and island grids. Here it's a question of reliability, of autarky, but especially in India, I think island systems are a very important issue in the areas where we don't have the interconnected system also over the next years. So this is a separate topic, I think, which requires a significant consideration. So thanks for your interest, and I'm looking forward for intensive discussions, maybe also after the session. Thank you.